Okay, so let's continue with the second part of Hongtaek on Hamiltonian flows on Hitchin components.
Thank you for the introduction. And as I promised yesterday, I'm going to talk about two applications of Goldman flows on Hitchin components. One is about the covolume of the mapping class group action on the Hitchin component, and the other one is the strong denseness of Hitchin representations. So the first application about this mapping class group action. But classically, let's say S is a compact orientable surface of genus at least bigger or equal to 2, then the total Weyl-Petersen volume of the Riemann moduli space of S is finite. This is the very classical result. And our main theorem is actually shows that this finiteness of the volume, where if you go to the higher rank Hitchin component, this Weyl-Petersen volume becomes the Atiyah-Bott-Goldman volume. And our main theorem tells us that this finiteness property just breaks down as soon as we go to a higher rank Teichmuller space. So the main theorem of myself and joint work with Seoyoung Choi is the following. So in this case, we are dealing with a closed orientable surface with genus at least 2. And our Lie group will be PSL n plus 1R, PSO n plus 1N, or PSP 2NR, with a real length at least bigger or equal to 2. In this setting, the total Atiyah-Bott-Goldman volume of the moduli space that is obtained by taking the quotient of your G-Hitchin component by the mapping class group action is not finite. So this is our main theorem. And the lesson that you have to take from this kind of main theorem is that, one of the main theme of the higher Teichmuller theory is to investigate to what extent does higher Teichmuller spaces resemble the classical Teichmuller space. And this theorem tells you that when it comes to the mapping class group action, the classical Teichmuller space and higher Teichmuller spaces are pretty much different. That's the lesson. And let me give you an outline of this, our main theorem. So let's say the capital pi is the projection of from your G-Hitchin component into the moduli space. And let's say N be a non-empty relatively compact open set in the Hitchin component. And take any non-separating oriented simple closed curve and take any Cartan subalgebra element Q. And then you construct the following sequence of open sets. Well, by the properness of Goldman flow that I showed last time, tells us that we can find a sequence of real numbers such that the open sets these open sets are kind of disjoint in the G-Hitchin component. And we show that Goldman flows preserve the Atiyah-Bott-Goldman symplectic form. So all of them have the same Atiyah-Bott-Goldman volume. So up to this point, we are very happy because if these sets are disjoint in the level of moduli space, then we actually win the game. But there's no reason for this. So these sets are not necessarily disjoint, pairwise disjoint in the level of moduli space. So what we actually going to do is to find a nice open set N and nice Q that makes these open sets are disjoint in the level of moduli space. And then we win the game. So that's what I'm going to do. So we have to find a nice condition on N and nice conditions on Q such that these sets are disjoint. That makes these sets disjoint. Okay? So what would be a nice N, nice open set N? To define this, we need to do some preparation. And we are going to construct a nice open set N for PSL NR Hitchin component first. And at the end of this section, we're going to come back to the other two cases. So for the moment, let's just assume that G is a PSL NR Lie group. And as before, we just take a a oriented non-separating, could be a separating, but just to make our life easier, just assume that this is non-separating. It doesn't really matter. An essential simple closed curve, say alpha. Because it's non-separating, we have a subsurface S naught obtained by chopping your surface by the simple closed curve alpha. And we define some quantity which will play the role of kind of length in the Hitchin component, which is defined as follows. So we pick an element in the Hitchin component and pick any essential simple closed curve X. Then the length of X with respect to rho is defined by the logarithm of the largest eigenvalue over the smallest eigenvalue. And this quantity is well defined in the sense that it doesn't depend on the choice of your rho prime in the conjugates class, and actually doesn't depend on the choice of your X in its isotopic class, neither is the orientation of X. So this is really well defined length in the world of G-Hitchin representations. So this is it. And you also need some map that from the G-Hitchin component of S, the G-Hitchin component of X naught. This was the this is the compact surface obtained by removing alpha from your surfaces, closed surfaces. Well, I haven't defined the Hitchin component for the compact surface in this talk, but this is you can define this Hitchin component for compact surface in a very similar way that we did for the closed surface. We just say a representation is Hitchin. If you can deform this representation to a Fuchsian representation, and you require that this deformation, this course of the deformation, you require that the boundary holonomials are kind of purely loxodromic. It's almost the same as the usual, closed surface case. So here's the proposition. So we have chosen alpha from the beginning, and this was a simple closed curve, essential simple closed curve. So you can extend it to a patch decomposition, which means I choose a maximum collection of pairwise disjoint simple closed curve, and you chop all this, remove all these simple closed curves, then you got the collection of pair of pants. That's the pants decomposition. And then there is a non-empty open set N in the G-Hitchin component, and a constant epsilon bigger than 0, satisfying the following three conditions. So first condition, let's say T and S are arbitrary real numbers, and rho and eta is in N, then what we need is the following property. So let's say beta is an essential simple closed curve that is not isotopic to alpha j. Then you measure the length of alpha j at this representation obtained by applying the Goldman flow for time t to rho, and we measure the length of beta with respect to the representation that is obtained by applying Goldman flow for time s to eta, and you take the difference. And we request that this difference is always bigger than the definite amount epsilon. That's the first requirement for our open set N. And next two properties basically say that your N does not contain any fixed point of the mapping class group actions. And I can say that the first property is really important. And once you achieve the first property, then the remaining two properties are you just shrink your set appropriately to avoid all the fixed points. So once you can achieve this, the remaining two are kind of easy. So I'm gonna show that there is such an open set that satisfies the first property. And the key theorem for this proposition is a Kolla-Lemma by Jason and Tengren, which states the following. So let's G be a PSL NR. So that's why we are concentrating only on the PSL NR case. And let's take any Hitchin component element law and take two essential simple closed curve that I didn't put the assumption that they should be intersect with each other. And then the following inequality holds. So it says that, okay, suppose that your length of x at low is very small. Then this fraction becomes very large. And because this sum must be smaller than 1, this quantity must be very small, meaning that the length of y at low must be very large. So that means there is a uniform constant delta of g, which depends only on your Lie group G, such that whenever x and y are intersecting, and if one is smaller than this constant delta of g, then the other curve must have a length bigger than delta of g. That's the upshot of our Koller lemma. And now we find a Fuchsian representation, say rho naught, that satisfies these two inequality. You can find this kind of Fuchsian representation very easily by using, say, Fenchel-Nielsen coordinate or Bonan-Dreyer's coordinate. Yes, this is you can do it very easily. So the property is that the length of alpha I and alpha j, they are Pence curves, and they are different whenever I and j are not the same. And you request all the length of alpha I curves are smaller than the half of the constant delta g. You can find this kind of Fuchsian representation. And because length varies continuously on the Hitchin component, you can perturb a little bit. So you find the neighborhood of n of your Fuchsian representation law of naught, such that the length of alpha I and length of alpha j measured at low and eta is bigger than epsilon whenever I and j are different. And because of this condition, we can also achieve this inequality easily. And if you look at the definition of the Goldman flow, you can observe that the length of a simple closed curve that does not intersect with alpha will never change under the Goldman flow. So you can easily put the Goldman flow here and there and have the same inequality here. Now suppose that we have an essential simple closed curve beta, which is not isotopic to alpha j. Then, because we are taking the Pence decomposition, this essential simple closed curve beta must be isotopic to another Pence curve alpha I other than alpha j, or must intersect some of alpha j curve, right? So for the former case, say beta is isotopic to another Pence curve alpha I, then this inequality tells us that this holds. And if beta is not isotopic to any of alpha j, then it must intersect some of alpha j. Then our Koller lemma, the first item and the last item, tells us that this inequality still holds true. So we get we have the open set n together with the constant epsilon, and you just shrink n a little bit so that it avoids any kind of what is that? The fixed point of mapping class group action. Okay, that's what I mean by nice open set n. And let me tell you why n is nice. I say n is nice that, and this is reason why. So let's say f is let f be an open set that we constructed in the previous slide. And suppose that there is a mapping class phi that satisfies this equation, this condition. Well, this condition is something that we want to avoid. And if n is just a random open set, then we don't know anything about our mapping class. However, because of our nice condition on n, if this happens, then our mapping class must be a power of the n twist along alpha. So we have a very good condition on the mapping class that, I mean, we have a very good control on the bad mapping class group elements. That's why I say N is a nice. Okay, here's a quick proof for this lemma. Okay, suppose that we have this. And then that means that you can find an element rho in this open set and element eta in that open set, such that phi of rho equals eta. And you measure the length of alpha with respect to eta. And this is the same as this guy. And if you look at the definition of the mapping class group action, this quantity is equal to this quantity. And then from the property of N, this phi inverse of alpha must be isotopic to alpha itself. Otherwise, these two quantities cannot be the same. These two quantity has difference at least equal to epsilon that we found in the previous slide. So this guy must be isotopic to alpha. That's to say phi of alpha is isotopic to alpha. And then you observe that this condition implies that, okay, phi preserves alpha. You can isotope phi so that it preserves alpha Z-wise. And then it acts on the subsurface that is obtained by removing alpha from S, that is S naught. So we can restrict the phi to S naught, then this condition implies this. And from the third property of our open set N, this forces that the phi restricted to S naught is identity in this mapping class. That means you can isotope phi to the identity map inside S naught. And this happens only when phi is a power of dentist along alpha. You just can imagine, like, you have a self-diffeomorphism. It preserves the alpha, and it is an identity on the neighborhood of S naught. Then that must be the dentist. You can imagine this. So we have this lemma, and now I want to tell you what would be a nice Cartan subalgebra element Q. To do this, I need to embed our Lie group PSO n+1n and PSP2n into PSL dr in certain ways. So, okay, let's define the following matrix, like 2n plus 1 by 2n plus 1 matrix, whose anti-diagonal entries are all 1, and we have all zeros elsewhere. This matrix, you can compute that this matrix has a signature n+1n. So if you collect all the matrices that satisfies this equation, it becomes PSO n+1n. And similarly, this guy gives you a kind of non-standard symplectic form on R to the 2n. Of course, they are symplectomorphic, but it's non-standard as it is. So if you collect all the matrices that satisfies this equation, then it will become PSP2nr. If you use this kind of non-standard embedding, we can identify the Cartan subalgebras of these two Lie groups as a subspace of the Cartan subalgebra of PSL dr, say. So the Cartan subalgebra of this guy becomes this, the set of all diagonal matrices whose entries are of this form. And the Cartan subalgebra of PSP2n is this set, the set of all diagonal matrices whose diagonals are of this form. Okay, a nice N should satisfy the following condition. We have to pick Q from the Cartan subalgebras of PSO n+1n or PSP2n, depending on the dimension. And it requests that, okay, Q is a matrix. It's a Cartan subalgebra element, but it is a diagonal matrix. And you request that this Q has at least 2 repeating diagonal entries. So for example, when G equals PSL 3R, this is essentially the unique choice. So we have to have we have that the sum of diagonal entries should be 0, and we have at least 2 repeating entries. So this is basically the unique choice. For other cases, we have a bunch of choices, but why don't you take the simplest one? So this is the simplest choice. 1, 0, 0, and -1. This element contained in a least Cartan subalgebra of any of these 3 groups. And we have a bunch of repeating zeros here. So that's the one, that's the simplest nice cube. All right, then the Goldman flow along alpha by this particular Cartan subalgebra element will be called the Bulging flow along alpha. And you just simply denote it by this fancy B with Q and T. All right, this is the nice Q, and I defined the nice N. And here's the key lemma for our main theorem. Okay, so this is a good time to ask a question if you have any. SL2 is a rank 1 case. So SL2 is a rank 1 case. So there doesn't exist the Bulging flow. There's only a twisting flow.
Such a two direction. We need this two-dimensional direction.
Yeah, I understand, but I was waiting for up to this slide. Was everything else working as to end and so on?
Yeah.
Before you understand.
Yeah, you can find.
Yeah, I can find. We have a real anchor and it's 2. Yes, this property, at least 2 diagonal entries must be identical. Before here, no, I don't need any higher rank assumption. This is the actual key point. We need to have at least 2 repeating entries. So that's where we need a higher rank condition. So here's the key lemma. Again, I'm assuming that G is a PSL n plus 1R with n at least bigger or equal to 2, higher rank setting. And let's say n is the nice offset that we found a few slides ago. And as before, large pi, capital pi is the projection map. And there is a constant d depending only on our open set n, such that the following 2 conditions are satisfied. So first condition tells us the following. So we let n flow by the Bulging flow for time t, and we just flow n by the Bulging flow for time s, and we assume that the travel time difference is at least bigger than equal to this constant d. Then we require that the image sets are disjoint in the level of moduli space. That's what we want to have. And the second condition is relatively easier, just saying that the volume of of this set is the same as the volume of the set downstairs. So this is what exactly this condition means. Or you can say that this open set is sitting inside the fundamental domain of the mapping class group action. So I'm gonna prove the first item, and the second item is kind of relatively easy. Okay, so here's the proof. We need some argument, but basically you can bring everything to the original set, so that it's actually enough to show that for sufficiently large enough t, the set, for sufficiently large t, the set obtained by applying the Virgin flow for time t and the original set n are disjoint in the level of moduli space. That's what we actually want to show. So the proof is basically by means of contradiction. So we just negate the conclusion. Then we get the divergent sequence of real numbers, T1, T2, and so on forth. And you have a sequence of mapping classes, Vi's, and sequence of elements, low i's, in the set N, such that this guy comes back to the set N. That's what exactly the negation of this conclusion. Right. So from the lemma, this is why we have a nice open set, right? So if this happens, we have a very good control on the mapping class. So phi must be a power of dan twist along alpha. So we can write it this way. And some people call this this trick as a Goldman's trick, which is basically saying that the mapping class group action, dan twist action, can be interpreted as a time one map of the Goldman flow. So you can basically write this as the time one map of the Goldman flow, and the flow matrix is given by the Jordan projection of your matrix. And you have some exponent here. And given this expression, we just unzip this notation. Then it becomes this. So this is a time one map of the Goldman flow, and the flow matrix is given by this complicated gadget. But if you look at this gadget, you see the following. So so everything is in the Cartan subalgebra. This one and that one are in the Cartan subalgebra of SL, say DR, right? So they are all diagonal matrices. We identify these diagonal matrices as a vector in Rn. And as a vector, this Q of G has at least 2 repeating entries. Whereas you recall the theorem by Labori and Fock-Goncharov saying that the Jordan projection, I mean, the eigenvalues of this low I of alpha, they are all distinct. Meaning that as a vector, this guy has the entry of this vector is never, there's no repeating coordinates for this vector. Whereas this guy has repeating coordinates. That means these two vectors are never parallel to each other. And in that setting, we can estimate the length of this vector. We just project it to the orthogonal complement of this guy. And because low i's are chosen in the relatively compact set, there must be some angle theta of n that is bounded and confined between 0 and pi. So we have this bound on the size of this vector. And we know that as I goes to infinity, ti goes to infinity. So this vector, the size of this vector goes to infinity, and that violates our properties of Goldman flows. So the upshot is that we can find those constants that satisfies this equation. Okay, then now we can prove our main theorem for at least for G equals PSL n plus 1 R. Maybe you can, now you know what I'm going to do actually. So you just choose a nice open set and the constant d of n from the key lemma. And you choose the sequence of real numbers whose consecutive difference is bigger than the constant dn. And you consider this sequence of open sets, and they have the same volume. And by the key lemma, these open sets are all disjoint in the level of moduli space. Therefore, their volume is bounded from below by the sum of all these things, and this is morally infinite. So that's how we prove our main theorem for PSL n plus 1 R case. For remaining cases, we actually reduce everything to the PSL n plus 1 case by using this lemma. So let's assume that now G is PSP2NR or PSO n plus 1n. And they are all matrix groups and they are embedded in PSL DR. So we have a defining representation, and this defining representation induces a symplectic form preserving smooth map from the G-Hitchin component into PSL DR-Hitchin component. And this is not just a smooth map, but it is actually an immersion, meaning that it sends a tangent space of this space to a tangent space of this space injectively. Or in particular, this iota D is a local diffeomorphism. And iota D commutes with the mapping class group action so that it induces a map between the moduli spaces. And also it commutes with the merging flows. And now this is an endgame. So we choose n and dn from the key lemma, and you have a sequence of open sets. They are all disjoint pairwise in the level of moduli space. And we use this immersion property to find an open set n of G from the G-Hitchin component whose image is sitting inside our set n. And then we let this n of G flow by our verging flow. Then we have the sequence of open sets of the same volume. But you can see that because of this property, commuting property, this open set is contained in this set, and this guy contained in that set, and so on forth. And because they are all disjoint, these sets are also disjoint. So we obtain a sequence of open set, disjoint open set, with the same Atiyah-Bott-Goldman volume, and that's conclude our main theorem. Any questions for this proof? Okay. Actually, by using the same technique, we can prove something more. I haven't defined the maximal representation, but here's a kind of quick definition for it. This is kind of another very well-known example of higher Teichmuller spaces. So in this case, our Lie group G must be something called a Hermitian type, meaning that its associated symmetric space carries a natural Hermitian structure. And by using this Hermitian or symplectic form, we can cook up the continuous bounded class of the second cohomology group of G, Lie group G. And then you if you have a representation of pi 1 of S to that Hermitian type Lie group, we just pull back this scalar class to give you to produce a two form. Produce an element in the second cohomology group of pi 1 of S. And you evaluate this second cohomology class at the fundamental class, then you get some number, which is called the Toledo invariant of the representation. And this Toledo invariant satisfies something called the Miller-Mood type equation, inequalities. And the maximal representation is the one that attains the maximal possible Toledo invariant. We collect all these maximal representations, then it forms some sort of component in the character variety, and we call this the maximal component. And the theorem says that, okay, we collect all this maximal representation, and this form a space. And of course, and it's not obvious, but the mapping class group also acts on this the space of maximal representation. So we can form this moduli space. And unlike to the Hitchin component, this space is not connected. It has various components. And you take any connected component of this space. If n is bigger than or equal to 2, then each connected component has the infinite total Atiyah-Bott-Goldman volume. That's our theorem, another theorem. And proof is more or less the same as the Hitchin case. We just find a nice open set n. And when you construct this nice open set n, we need to have a Kolla lemma. Unfortunately, we have a Kolla lemma for maximal representation due to Berger and Posetti. And use this Kolla lemma, we can construct some nice open set. But Again, unlike to the Hitchin case, its maximal representation has some sort of singular points, a lot of singular points actually. So we need to handle this subtlety a little bit. But yes, we can. There are some difficulties, but we can kind of overcome this by analyzing the singular points a little bit. So we can prove this, and well, because maximal representation and Hitchin representation are all well-known example of higher Teichmuller spaces. So we can kind of conjecture that any higher Teichmuller space has kind of infinite Atiyah-Bott-Goldman volume, provided the associated Lie group has a higher rank. For example, we haven't covered this case, but we suspect that the same conclusion holds for any Lie group like PSO and NN case, or any exceptional Lie groups. And the G-Hitchin component for those Lie groups also have the infinite Atiyah-Bott-Goldman volume. That's kind of we can suspect. A more kind of ambitious question might be this. So we collect all the zeta positive representation that I guess Tengren introduced. That maybe, yes. So this positive representation, they are all models of a higher Teichmuller space. If your Lie group has a higher rank, then every component of this moduli space has infinite Atiyah-Bott-Goldman total volume. That's kind of our conjecture, but we don't have any nice idea to attack this kind of conjecture yet. So this is the first part of my our main theorem. And the second part of, okay, before we move on to the second application, please ask a question if you have any. Yes, more or less, yes. I think so. Although there might be some difficulties coming from this singular point problem, but I think that's the most hardest part, I think. Once you can prove some Kollalemma kind of thing for those cases, you can basically solve this problem. Yes. Okay. Okay, now let's move on to the next application. And I have like 10 minutes, so like to be a little bit slow. So the second application is about strong denseness of your Hitchin representations. The notion of strong dense representation is first introduced by, I hope I can pronounce his name properly, Brilia, Green, Gulanik, and Tao. I hope this is the correct pronunciation. It's a French actually. So yes, they introduced the notion of strong dense subgroup in an algebraic group. And this is kind of a representation version of strong dense subgroup. So we have a representation rho. And suppose that we have, let's choose two non-commuting elements x and y in your Pioneer S. And we look at the subgroup generated by rho of n and rho of y and take the Zariski closure of it. It may or may not generate the Zariski dense subgroup, but if it happens to generate Zariski dense subgroup in G for any choice of non-commuting pair, then we call this representation strongly dense. And relatively recently, Longreed and Wolf, they proved that the PSL and our Hitchin representation are generically strongly dense. And our main theorem is a generalization of their result as well as a partial generalization of their result. So let's say let G be any split form of a complex simple adjoint group. That's the setting where we can do some Hitchin stuff. And then the set of all G-Hitchin representation are generically strongly dense. Okay, obviously this generalized their result. And in their paper, they found the strong dense non-abelian free subgroup in various algebraic groups. And by using this strong dense Hitchin representation, which is generic, we can produce a strong dense surface subgroup in those Lie groups. So this is a kind of partial generalization of Brilliard, Green, Gurlenick, and Tau. All right, let me outline the proof. So this Hitchin bar is the set of all G-Hitchin representations. And fractals A is the Cartan subalgebra of the real algebra of G. And you consider the following set, U of alpha of X of C, which is the set of all G-Hitchin representation that satisfies this equation. And also, we consider the set of bad representation with respect to X and Y, the set of all G-Hitchin representation, rho, where rho of X and rho of Y generate non-Zariski dense subgroup. So this is a bad set that we want to avoid. And it's actually known that this set is Zariski closed. So what we need to do is to show that these bad sets are always proper for any choice of non-commuting pair X and Y. So of course, proof goes like by contradiction. So we negate this condition, then there must be some non-commuting pair X and Y, whose bad set is everything. Under that assumption, you can find a finitely many functionals on this Cartan subalgebra, such that finitely many functionals together with some non-empty open set in G-Hitchin representation, such that this open set is contained in this open set. Well, because the U alpha X and C is a proper analytic subvariety, that's something that we will prove in a minute. This can never happen because this is a proper algebraic analytic subvariety that it cannot contain any open set. So this is a contradiction. So the key point is to show that actually this set is non-empty. This set is always proper for any choice of alpha X and C. Right, to prove this, we have to revisit our Goldman product formula. So this Goldman product formula is to compute the Atiyah-Bott-Goldman product between two Hamiltonian vector fields. However, if you look at the definition of Hamiltonian vector fields, it actually tells us this. So this is almost by definition, and this product is the same as the first derivative of function g of y in the direction of Hamiltonian flows. Right? This Hamiltonian flows is associated to this Hamiltonian vector field, and it initiated law. And this is the kind of reinterpretation of this gadget. And in this sense, Goldman product formula is kind of a first variation formula for certain functions. So with this interpretation in hand, well, in the Goldman product formula, we have to assume that X and Y are simple closed curves because we have to have this Hamiltonian vector fields. This Hamiltonian vector field or Goldman flow is not defined for non-simple closed curves. But if you look at this gadget, there's no reason for Y being simple. So using this kind of observation, we can prove the following theorem. Now, Y is just oriented essential simple closed curve. It's not necessarily simple. And X need to be simple again because we have to do some Hamiltonian flow stuff. So X is an oriented essential simple closed curve. Y is just essential closed curve. And let's say X, F, and G are invariant functions. And then this first derivative can be computed by using this summation. This is almost the same as the Goldman's product formula, but the point is that Y is not necessarily simple here. Of course, we cannot put omega of like X of, we cannot, yes, this is this. All right, well, how to prove it? Well, if Y were simple from the beginning, we just use the Goldman product formula. But if Y is not simple, this is kind of standard procedure. So if your curve Y is not simple, then we just take a finite covering of S so that it resolves all the singularities of Y. And then Y leads to a simple closed curve in the covering S of Twitter. And then in this covering, X will be lifted to some collection of multi-curves. And the Hamiltonian flow for this simple closed curve X will lift it to the Hamiltonian flows along the multi-curves. And if you remember the last talk, the Hamiltonian flow along like what is it, non-intersecting simple closed curves are always commutative, and their associated Hamiltonian vector fields can be written as the summation of individual Hamiltonian vector fields. We should have some multiplication factor here, but I just ignore it. It's just not very essential. And now we have a simple closed curves, and Y is also Y lifted to a simple closed curve again. So we can use the Goldman product formula on the covering space as Twitter, and then we do some computation to get this formula. Now we use by using this first variation formula, we can compute the following thing. So as before, Y is any oriented simple closed curve, not simple. Y is the oriented closed curve, and X is the oriented simple closed curve. And let F be a composition of some functional and the Jordan projection. This kind of invariant function, we studied these types of invariant function in the yesterday's talk. And let's say phi be a function representation, and let's say rho phi be a Hamiltonian flow associated to this Hamiltonian vector field. And then the first derivative of this function along this Hamiltonian flow can be computed by the following summation. The sum is taken over all the intersection points between X and Y, and alpha was the dual of alpha. V is the dual of alpha with respect to B. And this guy is just an image of the rotation matrix. And the argument here is the kind of angle between the geodesic representative of X and geodesic representative of Y, and the angle measured with respect to the hyperbolic structure associated to rho. Sounds very complicated, but the situation is kind of simple. So anyway, we have to compute this quantity from the Goldman product formula. And if you look at, we know the value of the Goldman function at the positive Weil chamber. And because of the theorem by Rabori and Konchaloff, you can always conjugate this element into the positive Weil chamber. And because B is not joint invariant, we just take the global conjugation so that this guy sits inside the positive Weil chamber. And we take the further conjugation so that the intersection happens at the unit imaginary point. Then we have this kind of, we just do some hyperbolic geometry, and you can see that this is the case. So the situation is like this. If you do such a normalization, our X, the geodesic representative of X, is this vertical line with an attracting fixed point at the infinity. And depending on the sign of the intersection, this is the case when the sign of intersection is -1. And then we have a geodesic representative of y. It must pass through the unit imaginary point. And it looks like this. And we have a attracting fixed point here because we have a negative sign. And the angle is from x to y in a counterclock manner. So we have to measure this angle. But if the sign is positive, we should have a same figure, but the attracting fixed appears here so that the geodash goes in this direction. Oh, I'm almost running out of time. So let me very quickly show that this is a proper open set. So the idea is very simple. So y is alpha x and c are given. So we take a essential simple closed curve that intersect at least once with x. And then we do some twisting flow along y. And then this is kind of folklore theorem. If you do the twisting enough, then the angle between x and y converges to 0. So we can find a large enough T0 so that this happens for every intersection points. And we compute this guy. And you can see that every sum end is positive. So we just like push this representation slightly out of the function locus so that we have this thing. I think I don't have enough time to go through this proof for the main theorem. But the idea is kind of, we use this classification of Sambarino, which says that basically saying that the Lie algebra of yeah, okay, I can explain this in a couple of minutes, so I have to stop. I think I have to stop here. Thank you.